Hello everyone, my name is Farhan and I am from SM batch, and I am here to present you a PPT on the fuselage stress. So we are going to see into the cabin with the pressure that affects the cabin or the fuselage of the aircraft. We are going to see the loads that apply on the cabin. So what are we looking for? So the topics that we are going to are the first one, that is the challenge of cabin pressure. So we are going to look for the loads and the stresses that the cabin or the fuselage experiences. Next is the stress distribution analysis that will be, we are going to analyze what are the stresses that are experienced by the fuselage. Then the next is the material science and fatigue, that is the what material can be best or what material we can use to reduce the stress or the loads that are applied. Then we are going to look at the design innovations and optimization. Then we have last one is the future frontiers in fuselage. So the pressurized world. So what is the pressure what is the stress that cabin or a fuselage experiences? So the fuselage, it maintains during a flight, it maintains approximately of 0.55 bar pressure, that is 8 psi, which is higher than our external ambient pressure, which is of around 2400 meters. So the load case for fuselage frames and the cabin pressure is the hoop stress, which attempts to expand the fuselage, but also we need the fuselage to be intact, so that while traveling in an aircraft we will be not feeling any uncomfortability, and we will comfortably travel. Also, now the next is our stress distribution. So the internal pressure that is created inside the cabin, we have a hoop stress that is been developing, and the stress concentration also it is particular in a cabin. We have the frame skin interaction. The skin of the fuselage, it interacts with, of course, the first thing that the pressure or the stress is applied on is the skin, and we have to make sure that the skin is very, it should be very strong and it should bear the weight and the stresses. Then we have the windows and the door cutouts. Of course, if we cut through a metal or any part, the stress applied on the cutout will be more than on the part, because it is a cutout. Of course, the geometric discontinuation, it affects it a lot. Then we have longitudinal stiffeners. The design for these are bending and axial loads, stiffeners that contribute to the load. They also contribute in maintaining the stress, so that the structural integrity should be maintained. Now we will look for the analytical methods. Historically, we had a lot of different kinds of the cabins or fuselage designs, in which monocoque, semi-monocoque are there. So if we look in the geometry, of course, it is a very complex geometry of a fuselage to maintain and to create such an intricate design to maintain the pressure inside, so that the structural integrity should be maintained. Now there are various methods that we can use to analyze the stresses. The first one is the FEA, which is the finite element analysis. This is currently, FEA is the most used analysis method. Every industry right now is using the FEA to calculate the stresses and the loads that are experienced by the fuselage and cabin, and also it gives us very precise calculation for loads and the stresses. If we can, the FEA can stimulate material plasticity, crack propagation, and fatigue rise also. Also, we have computation fluid dynamics, that is the CFD. It is very general method that is used, and CFD can model the pressure analysis due to the external pressure that is applied on the cabin. Then we have the experimental testing, which is the physical testing of a part. The companies or the industries, they take one part of the fuselage, they do some testing, the physical testing on the part, and they can calculate the stresses that act on it. Then we have material science and fatigue fight. So generally, if we look at the materials that are used earlier for the fuselage, then it was the aluminium alloys, and they were the backbone. They were the backbone for fuselage construction because their strength to weight ratio is very favorable for a fuselage. Also, it's lightweight, so it was the best material to use for the fuselage. But as the development goes on, as the technological advancements we make, we find out different methods to make different kind of materials and composites of different kinds. So we have composite materials in which CFRP, which is the carbon fiber reinforced polymer, which currently is the best material which can be used for making the aircraft fuselage. So of course it has a very good strength to weight ratio, better than aluminium alloys. Also, it is lightweight, it is corrosion free, so it ultimately reduces the maintenance of the industry. Then we have design innovations, optimizing for safety and efficiency. So of course, safety is the most important factor in aircraft. We are traveling 10,000 feet above, so we need to ensure that our flight is safe. We have 200 passengers or 300 passengers to look after, and the engineers, they have made sure that the safety should be the most important factor. And we have integrated structures, that is the fuselage sections. We can make larger sections of fuselage so that we can reduce the fasteners and the bolts. So the stress applies directly on the metal and not on the fasteners, which can ultimately increase the structural integrity. Then we have stiffened panels. They optimize stringer and frame spacing along with stiffener geometries, for example Z stiffeners or hat stiffeners. This can efficiently carry the loads. Then we have additive manufacturing, that is 3D printing. Nowadays 3D printing is widely used to make parts because it is made from scratch and it is a single part. It is not made by combining 3 or 4 different parts or multiple parts, but it is a single part. So the structural integrity in this part, it is the best, it is the most. So these can be the most used thing. Next we have case study. A case study on Boeing 787 Dreamliner, which is the prime example of today's aircraft. If we look at Boeing 787's fuselage, it is a single, what we can say, it is a one-piece barrel construction. That is the CFRP, the polymer. We can make its fuselage with a single barrel of the sheet, and it looks. It minimizes the fasteners, the joints, which can ultimately, of course, it potentially reduces the fatigues and the stress applied on the fuselage. The next is we can get because of the composite frame, because of the composite polymer, have excellent corrosion reduction that ultimately leads to the reducing in maintenance, and of course it is beneficial for the companies. Then we have cabin pressure. Of course, we can maintain a cabin pressure at 1800 divided by 1800 to 1800 meters, that is 600 feet, and it can enhance the effects of altitude sickness. So future frontiers. There are a lot of points which can be looked at this. We have AI driven optimization, we can use machine learning, we can using machine learning we can rapidly explore in this, and we can increase the strength to weight ratio, we can decrease the weight of the aircraft, then we have sustainable manufacturing, we can reduce environmental impact of fuselage, we can use a polymer that doesn't harm the environment. Then we have self-healing materials. If we can, there is research going on these materials, that is the self-healing materials, which can heal the microscopic damages that happen on the aircraft, which will be the most beneficial thing, because it will reduce the maintenance at a very big impact. It will be a very big impact on aeronautic industries. Then we have integrated sensors which will be embedded fiber optics or piezoelectric sensors which can directly go into the fuselage structure, and we can monitor stresses and all. Then we have the key takeaways. What we can take away from this presentation. So we saw about complex load environment, that the stresses or the loads that are experienced by the cabin pressure, the hoop stresses and all. Then we have advanced analysis, that is FEA, which is indispensable. FEA is the best method right now which can be used to understand the stress and the loads that are affecting the cabin or the fuselage of an aircraft. Then we have material evolution, how we move from aluminum alloys to CRPs, and currently, of course, research is going on. We are looking for a more lightweight and more hard, or you can say more strong material, which can be, through which we can develop a design which can reduce the fuel usage and all. Then we have continuous innovation going on regarding the aerodynamics of the aircraft. So thank you for visiting and for looking on my presentation.